Let's look at another example of showing two matrices are row equivalent. So here I want to show that the identity matrix is row equivalent to the matrix A. And this is the 3 by 3 identity matrix, and here's the matrix A. So what I want to do is I want to show that I can get to the matrix I by multiplying A by a sequence of elementary matrices. Now at the moment, I'm not telling you how many elementary matrices there are, but I'm telling you that there's a certain amount of them, and we can multiply A by these matrices to get the identity matrix. So let's see. Let's look at this matrix A and think about what we need to do to it to make it look like this. In other words, if we put it in reduced row echelon form, we should get the identity matrix. So let's put A right here. Let's rewrite it. So it's 1, 1, 2, 0, 3, 4, 2, 1, 2. And what is my first step? Well, what I'm going to do, now you can do this however you want as long as you get to the identity matrix. But what I'm going to do is I'm going to get rid of this 2. So that means I need to take negative 2 times row 1 and add it to row 3. And this is going to be my first elementary matrix. Okay, and I'm going to actually write this on the top. So this is negative 2, negative 2, negative 4. And I'll get 0, negative 1, negative 2. And over here on the side, I'm going to actually write out what E sub 1 is, this elementary matrix, because I'm going to have several of them and I don't want to get confused. So I took negative 2 times row 1 and I added it to row 3. So this is E sub 1. Okay, let's continue. Now how do I take this matrix? What should I do next to make it look more like the identity matrix? Let's see, I want to get rid of this 3. I want to make it a 1. So what I'm going to do is I'm going to multiply the third row by 2 and I'm going to add it to row 2. And this is going to be my second elementary matrix. Okay, I'm going to put this down here. This is going to be 0, negative 2, negative 4. So I'm going to end up with 0, 1, 0. Okay, and then again I'm going to write what E sub 2 is off on the side. So we took 2 times row 3 and added it to row 2. Great. Let's put a little line here so we can continue this. Let's see. Notice that I have a 1, 2 here and a negative 1 and negative 2. So if I just add row 3 to row 1, it's going to cancel these out. So I'm going to take row 3 and add it to row 1. This will be E sub 3. And I'll get 1, 0, 0, 0, 1, 0, 0, negative 1, negative 2. And let's write what E sub 3 is. This is going to be 1, 0, 1, 0, 1, 0, 0, 0, 1. Taking row 3 and I'm putting it in row 1. I think we can finish this in 2 steps. I need to get rid of this negative 1, so I'm just going to add row 2 to row 3. That'll be E sub 4. Okay, let's write that down. So E sub 4 was we took row 2 and added it to row 3. And then our last step would be just to make this a 1. So we're going to divide by a negative 2. So negative 1/2 times row 3 will give us the identity matrix. Okay, and so this will be E sub 5. And we're going to write e sub 5. I'm going to put it right here. So 1, 0, 0, 0, 1, 0, 0, 0, negative 1/2. Okay. So what have we shown? Well, we have put the matrix A into reduced row echelon form, and the reduced row echelon form is the identity matrix. So the identity matrix is equal to e sub 5 times e sub 4, e sub 3, e sub 2, e sub 1 times A. And you could double check this. You can multiply all of these out and see if you get the identity matrix. But you should if we did everything correctly. All right, so we showed that the matrix A was indeed row equivalent to the identity matrix, or the identity matrix is row equivalent to A. It doesn't really matter because if you can show that one is row equivalent to the other, so if A is row equivalent to B, then B is row equivalent to A. You just do the inverse of all of these properties. So this is interesting. I want to mention something really neat about this. So what we've done is we've multiplied all of these matrices together to get the identity matrix, but remember that matrices are associative. What if I just multiply these right here? So we'll get a matrix, let's call it B, and we can say that this matrix B times A is actually equal to the identity matrix. Well, we found a matrix that when we multiply it by A, we get the identity. That means that this matrix here is actually A inverse. So A inverse is a product of elementary matrices. Isn't that neat? So it turns out that any matrix that's invertible, the inverse is a product of elementary matrices. And in fact, if the matrix is invertible A, that matrix too is a product of elementary matrices. That's going to be our next theorem. So whenever I give you a matrix and I ask you to find the inverse, you can use this process to find the inverse. You just multiply all of these elementary matrices together and that will give you the inverse.